Okay, so we're going to do a couple of examples to continue in our lesson on motion. The first of which says that if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is given by the position function s of t, which is equal to 80t minus 16t squared. So this is a two-part question. Part A asks, what is the maximum height reached by the ball? And part B asks, what is the velocity of the ball when it is 96 feet above the ground on the way up and then on the way down? Okay, so we can do part A here in two ways. So first way we can do this is not using calculus at all. And the second way is using calculus. So let's talk about how we can do this without using calculus. So if you look at the position function, that function s of t, that function is a quadratic function, so it's a parabola. And because the coefficient of the squared term is negative, that means that the parabola opens down. So if we want to find the maximum height reached by the ball, one way of doing this without using calculus is to figure out what the coordinates of the vertex are going to be. So the first coordinate, the t value, is going to be time. And then when you plug that into our function s of t, that's going to give you the position or height at that time. Okay, so if we want to calculate the coordinates of the vertex, the first coordinate t is going to be negative b over 2a. Okay, so negative b is going to be the coefficient of the linear term, the opposite of that. So the opposite of 80 is negative 80 over 2 times a. And a is the coefficient of the squared term, which is negative 16. So this becomes, since both the numerator and denominator are negative, that's going to make, like when I eliminate those negative factors, that can make them both positive. So that's 80 over 32. And both 80 and 32 are divisible by 16. So 16 goes into 85 times. 16 goes into 32 twice. Okay, so the time that the ball reaches its maximum height is at 5/2. And then if we actually want to find the maximum height, we can plug 5/2 into the position function, and that's going to give us the height at that time. Okay, so if we take s of 5 over 2, and that's going to be 80 times the quantity 5 over 2 minus 16 times the quantity 5 over 2 squared. Okay, so 2 goes into 80 40 times, and then 40 times 5 is 200. 5/2 squared is 25 over 4, so 4 goes into 16 4 times, and then 4 times 25 is 100. So 200 minus 100 is equal to 100. Okay, so this first coordinate here gives us the time when the ball reaches its maximum height, and then the second coordinate gives us the height at that time. So the maximum height reached by the ball here is going to be 100 feet. Okay, so that's like one way of working this problem out, not utilizing any calculus at all. Okay, and that's a totally valid approach for us to do part A. Okay, so let's look at how we can do part A utilizing calculus. I'm going to go ahead and get rid of this. So if I want to use calculus, if you think about like the ball being thrown upward, when the ball gets thrown upward, when it reaches its maximum height, like the ball is going to go from having a positive velocity because the ball is moving upward. Once it reaches its maximum height, it stops for a split second, okay, when the ball reaches its maximum height. And then when the ball falls back downward, the velocity is going to be negative, okay? So we can determine the time when the ball reaches its maximum height by calculating the time for which velocity is going to be equal to 0, okay? So given the position function s of t, which is equal to 80 minus 16t squared, we can find the velocity function by taking the derivative of the position function. Sorry, that should be 80t. Okay, so the velocity function is going to wind up becoming 80 minus 32t. And then if we want to calculate when the ball reaches its maximum height, that's going to be when the velocity is equal to 0. Okay, so that occurs when 32t is equal to 80, which means t is equal to 80 over 32. And again, 80 and 32 are divisible by 16, so that becomes 5 halves. And then if we want to actually find the maximum height, we're going to take the position's value s at 5 halves. And then again, we just calculated that earlier. We found that to be 100 feet. So that is the maximum height that is reached by the ball. Okay, this time we used calculus in our approach to determine that. The previous way we worked it through, we just used algebra only. Okay, so part B. Question asks, what is the velocity of the ball when it is 96 feet above the ground on the way up and on the way down? So if we picture our ball here, our ball being tossed upwards reaches its maximum height of 100 feet. And then we're trying to calculate when it hits 96 feet on the way up. And then also when it hits 96 feet on the way down. Okay, so we want to determine the times for which those, for which that occurs, and then we're going to calculate the velocity at those times. So if we want to calculate the time for which it occurs, we want to find when our ball is 96 feet above the ground. So we're going to plug 96 in the place of s of t. Okay, so we're going to get 96 is equal to 80t minus 16t squared. So we have a quadratic equation here. We're going to move all the terms to one side. So I'm going to move all the terms to the left-hand side. Get 16t squared minus 80t plus 96 is equal to 0. And when we look at all three of those terms, look like they are divisible by 16. So if we factor 16 out, we're left with t squared minus 5t plus 6 is equal to 0. And that quadratic equation factors to t minus 2 times t minus 3. So our times for which that occurs is at t is equal to 2 and t is equal to 3, which, if you think about it, it should make sense because we found in part A that the ball reaches its maximum height of 100 at t is equal to 5 halves. So it's going to reach the height of 96 on the way up at t is equal to 2, and it's going to reach the height of 96 on the way down at t is equal to 3. Okay, so once we determine these times, the question asks what is the velocity of the ball at those times. So we're going to take these two times and plug them into our velocity function. Okay, so v of 2 is going to be 80 minus 32 times 2, and that's going to become 80 minus 64, which is equal to 16, and then our unit of measure is feet per second, which, if you think about it, at time t is equal to 2, the ball is traveling upward, so the velocity should be positive at that time. Okay, and then we can also calculate the velocity at time t is equal to 3, which is going to be 80 minus 32 times 3, which is 80 minus 96. So that's going to be negative 16 feet per second. So our ball is traveling downward at time t is equal to 3. So the velocity should be negative, and the velocity is in fact negative at that time. Okay, so that answers that both parts of that question right there. Okay, let's move on to the next example. So the directions for this next one ask us to use the graph of s of t, so that's the graph of a position function, to answer the following questions. Okay, so we're given the graph of the position function in red. So part A asks, when is the particle moving to the left? When is it moving to the right? And then when is the particle stopped? Okay, so if you guys remember back in class, we said that the direction of motion is dictated by the velocity of our function. So if we are given the graph of the position function, if I want to determine velocity, we know that velocity is the derivative of position. Okay, so if we're trying to determine the derivative of this function that is graphed, we have to be looking at the slope of our graph. Okay, so when the graph has a positive slope, I'm going to highlight that in yellow. Okay, so when the slope is positive, the graph is going to be moving forward. When the slope is negative, I'm going to go ahead and draw that in blue. So when the slope is negative, the graph is moving backward. Okay, so it's negative at those two segments. And when the slope is 0, our particle is going to be stopped. So I'm going to draw that in purple. Okay, so when are we moving to the left? So we're moving to the left when v of t is less than 0, so when the slope is negative. So on what intervals does that occur? Well, that occurs on the interval from 2 to 3, as well as the interval from 5 to 6. Now, with your endpoint of 6, you have the option of making that a parenthesis or a bracket at the end. Okay, it's your choice. Okay, so parenthesis or bracket would be acceptable for that last value. But we have to have parentheses at the other point. So we have to have parentheses. I'm going to go ahead and draw these points here in black. Okay, so we have to have parentheses here at 1, here at 2, here at 3, and here at 5. Because when we look at that position function, if we're looking at the derivative of that graph, the derivative is undefined at those 4 points because our graph has corners at those points. Okay, now again, the points that I have highlighted in light blue here, so this point at 0 and this other endpoint over here at 6, if you want to use a bracket or a parenthesis at those endpoints, it does not matter. Okay, either one of those values are okay to use parentheses or brackets at, but the other corners at 1, 2, 3, and 5, we have to use parentheses at those values because our derivative is undefined at those points. Okay, so if we want to determine where the particle is moving to the right, that's going to happen where velocity is positive, so that occurs on the interval from 0 to 1. You have to use a parenthesis at 1 because the derivative is undefined there, but at 0, it's your choice whether you use a parenthesis or a bracket. Either one of those is acceptable. And then our particle is still when the slope or the velocity is equal to 0. Okay, so our particle is still where the velocity or the slope is 0, which occurs on the interval from 1 to 2, and also on the interval from 3 to 5. Okay, so if we want to graph the particle's velocity, that's asking us to graph the derivative of the position function. So what we want to do is we want to calculate the slopes on each of the, I'm going to draw this in black here, on each of the 1, 2, 3, 4, 5 segments. Okay, so we want to calculate the slope on each of those 5 segments. Let me go ahead and draw this real quick. Okay, so this is going to be the t-axis. This is going to be our velocity readings. And then when we look at the first slope that's highlighted in yellow, the slope of that segment is going to be 2. Okay, so again, it's your choice whenever you draw the derivative here. If you want to use a closed dot or an open dot at the starting point, it's entirely your choice. I'm going to use an open dot here, okay? And then all the slopes between 0 and 1, all those points are going to have a slope of 2, okay? So that means the y-coordinates of all those points are going to be 2, okay? If I look at that purple segment, okay, so the next segment, between 1 and 2, the slope of that segment is going to be 0. So when I look at the derivative, all of those points between 1 and 2 are going to have a y-coordinate of 0. When I look at the next slope, the light blue one, I've gone down 4 units and I've run 1 unit. So the slope there is -4. So all the points between 2 and 3 are going to have a y-coordinate of -4. When I look at the next purple segment, all the points between 3 and 5 have a slope of 0. So that means that on the graph of the derivative, all the y values between 3 and 5 have a y-coordinate of 0. And then when I look at the last light blue segment, all the points between 5 and 6 have a slope of -2. So that means that all the y-coordinates on the graph of the derivative between 5 and 6 are going to be -2. Again, if I want to use a closed dot at the end point, that's fine. At 6, if I want to use an open dot at that point, that's acceptable as well. Okay, so that's the graph of velocity. The only thing that's going to change whenever we graph speed, speed is the absolute value of velocity. Okay, so if we want to graph speed, we would just take these parts of the graph here that are negative, and then we would reflect that graph across the t-axis. Okay, so that would put like points up here at 4, between t is equal to 2 and t is equal to 3, and that would put the points between 5 and 6 up here at 2. Okay, so if we wanted to graph speed, I would erase the parts of the graph in green and then replace them with the parts of the graph in purple. Okay, last thing I'm going to have you guys do is I want you to get this example copied. So we're going to go over this example after the quiz that we take on Thursday and Friday. Okay, so the directions here say to use the graph of v of t. So this is different here. In the previous example, we were given a position graph. This time we are given the graph of velocity. Okay, so we're going to use the graph of v of t to answer the following questions. Make sure you sketch that graph accurately. So part A asks, when does the particle reverse direction? Leave yourself a little bit of space in between all of these parts. Okay. Part B asks us to graph speed. Part C asks, when does the particle move forward? When does it move backward? And when does it stand still? Part D, when is the acceleration positive? When is it negative? And when is it 0? For part E, question asks, when does the particle move at its greatest speed? For part F, when does the particle speed up? And when does it slow down? And then for part G, we're asked to graph acceleration. Okay, so again, just get this example copied down, leave yourself a little bit of space between each of those parts, and then we're going to answer these together in class after our quiz on Thursday and Friday. Okay, so this should give us enough time in class to complete this last example after our quiz, and that'll be it for this lesson. So we'll see you guys in class Thursday and Friday. All right, take care, everybody. Bye.